So part 3 of chapter 14, we're going to be focused on concentration and time. So in the first video, we looked at, At the first video, we looked at vocab terms, the different types of rates, and we talked about how reactions slow down over time. So they're the fastest at the beginning and then they slow down over time. Now in the second video, we looked at the relationship between concentration and rate. So if I change the molarity, how does that impact the rate, the speed of the reaction? Well, we do know that in general, you increase the concentration, you increase the speed, but we were able to have a mathematical relationship that we had to build for every reaction for each chemical based on its concentration, and those were the rate laws. Okay, and we were able to figure out the order of each chemical based on the rate law. Is it first order, meaning it would be raised to the first power? Is it second order, meaning it's raised to the second power? We didn't run into any, but another option that sometimes happens is zero order, which would be raised to the zero power, which means that when you change the concentration, the rate does not change. So what we're going to look at in this video is when we're looking at a specific reaction and we're following it, so it's happening over time. We want to be able to predict what the concentration of a chemical would be after a certain amount of time, once the reaction has begun, or predict how long will it take for a reaction to decrease its concentration down to a certain value. Okay, so we're focused on time, lowercase t, and concentration. Now, the mathematical equations we're going to be using in this area, they came from chemists using calculus. Now, calculus is not a prerequisite for this course, so I'm not going to give you the background on where these equations come from. You're just going to have to believe me that I'm giving you the correct equations, and then you're going to learn to use them. So these equations, you don't need to memorize them. I will provide them for you, but I will not, when I provide them for you, I'm not going to tell you which scenario in which to use them, and I'm not going to tell you what the variables, the letters, stand for. So those are the things you have to get good at. Now, there is a different equation depending on the order of the chemical. So if we're trying to figure out how much chemical will be left after 5 hours, well, I need to know that chemical. Well, is it a zero order chemical, a first order chemical, or a second order chemical? So we have multiple equations here depending on the order of the chemical. The order of the chemical can be determined if you were told the rate law. All you have to do is look at that chemical in the rate law and see what its power is. Is it a 0? Is it a 1? Is it a 2? It could just be told to you in the question, oh, this chemical, which is first order, blah, 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 blah. And then you would know that it's first order. And if someone's being ridiculously tricky, which sometimes mastering chemistry does, the only clue that's given to you are the units of the rate constant. The lowercase letter k that is in the rate law, sometimes we have to look at those units and based on those units, figure out the order of the chemical. Now that will not be the way the information is given to you on an exam or even in a discussion worksheet, but it could happen in mastering chemistry when you're able to use your resources. Okay, so we're going to first go through all of the equations, and then at the very end of the video, we're going to practice doing some example calculations using the equations. But first, we're going through them. We're going to look at each equation, talk about each equation until we've looked at every single equation. Then we will put it together and read questions, decide which equation to use, and practice doing the math. Okay, so these are called the integrated rate laws, because they used calculus and they integrated things in order to do that. So here's the first integrated rate law, although I'm going to rearrange it so it looks a little bit different here in a second. It's the same equation, but I'm just going to rearrange it. But first, let's point out what all the letters or the symbols stand for. So the brackets stand for molarity. Okay, so I have two molarities in this one. A capital letter A, which always just stands for the chemical that you're looking at. So depending on the question, you wouldn't write A, you could write HCl or NaBr, whatever chemical we're looking at. Okay, but there's two of them with the brackets and the A. One of them has a subscript T on the outside and the other one has a subscript 0 on the outside. The 0 represents the initial concentration. That 0 means time 0 at the beginning. How much was there at the beginning? The one with the subscript T, lowercase t, is standing for time. So that's the molarity after some amount of time, which that amount of time would be specific based on the question that you're being asked. The ln right here stands for natural log. It is a mathematical function. If you look in your calculator, you should have an log, a base 10 log button. You will also have an ln button. If you don't have a scientific calculator, and you need to get yourself one of those because we're going to be using that natural log. So when we're looking at that as a mathematical function, okay, the inverse of natural log, like the way to get rid of natural log, to cancel out natural log. If you look at your calculator and you find your ln button, the second ln or shift ln, or depending on how your calculator works, whatever the button you have to push to give it the other operation, should show e to the x, so it looks like this, or something like that. That is the inverse of natural log. E to the power of is the inverse of natural log. So when we're doing this, I'm just reminding you of that really quickly, but you're going to be expected to calculate using this and solve for any of the 4 variables: a with a subscript t, a with a subscript 0, k, which stands for rate constant, just like k stands for rate constant in the rate law, and then lowercase letter t, which stands for time. So the rate constant and the time will both have time units. We just need to make sure they are the same time units in them. Okay, like if they're both seconds, they both contain seconds, or they both contain minutes, or they both contain hours. If one of them contains seconds and one of them contains minutes, you need to get one of the values converted so that way they are both the same. Okay, so what we're going to do now is I'm going to rearrange this equation. What I want it to do is I want it to look like a y equals mx plus b equation. So one thing on the left, something times something plus something on the right. So based on log rules, okay, the natural log of a sub t over a sub naught, a sub 0, is basically, it's just subtraction between them. So then I'm going to rearrange this, leaving me in this format. So what this lets me do, this equation is the same, the top equation is the same as this first one. Okay, they're the same equation, they're just rearranged. In this y equals mx plus b, what this lets me know is that for a first order reaction, if I were to graph the set of data that I have, I would see a straight line when on the y-axis I have the natural log of the molarity, and on the x-axis I have time. So I will see a straight line when I graph the natural log of the molarity on the y and the time on the x. The slope would be of the graph, like if I were to graph it and get my data from Excel, the slope would be the negative k value, so that would be a way I can figure out the rate constant. And then the intercept would be the natural log of the initial molarity. Okay, this equation only works for first order chemicals though. So if a chemical is 0 order or second order, this equation doesn't work, which means it wouldn't make a straight line. So I'm going to show you this equation. The way this equation will be given will look like this. Okay, I'm going to leave it in this format. But something that you're going to need to know, other than being able to use the equation, which we'll practice here in a minute, is that if I were to give you a graph of a set of data, and I had taken that data and set up the graph, maybe I give you 2 or 3 graphs, okay? The way you would recognize when a chemical is first order graphically is when the y-axis is the natural log of the molarity, the x-axis is the time, and when those 2 things are true, the graph is going to have a straight line if it is first order. If it is not first order, then we won't see a straight line. It'll be a curve or I don't know why it'd be a wiggle, but a wiggle or something that's not a perfectly straight line. Now, it will have a negative slope, so the line's going to be going down. Okay. But if we make a graph with natural log of molarity on the y-axis, time on the x-axis, and I get a straight line, that tells me something is first order. So, like, why would anyone ever do that? Well, in the last video, when we figured out the rate law in order to figure out what order something was, we needed multiple experiments. I think both times I gave you 5 or 6 experiments in the table. Well, maybe someone didn't do the experiment 5 or 6 times. Maybe they only had enough chemical to do it once. And they wanted to figure out the order of the reactant. Well, this would be one way to do it. With your set of data, take your set of data with a bunch of different numbers on it and graph it, and we can figure out if it's first order. Okay, so in this example, I'm telling you up front, this reaction is first order. And one way I can prove that, if I take the data, so instead of molarity, this one's a gas, so they used pressure. So we're going to consider that like molarity. Okay, this time they graphed it by putting on the x-axis time, and on the y-axis, I'm going to say molarity, even though it's really pressure. Now, if we look at this, the dots and then the line connecting them. That is not a perfectly straight line. Okay. So hopefully we can recognize that. That's not a perfectly straight line. Well, that was interesting. Let's check to see if it's first order. So in order to check to see if it's first order, I'm going to take the same data, but the y-axis I'm going to change. The y-axis is going to be the natural log of the molarity, and the x-axis is going to be time. And when I did that, that's this one. Okay. Do you see how the data points became a perfectly straight line? It's got a negative slope. Okay. So that is indicating to me that it is first order, because when the y-axis is natural log of something and it's a straight line, that tells me it's first order. We're going to keep looking at these as we go to our next equation. So hopefully if it's still like kind of fuzzy, hopefully by the end of this, you'll feel a little bit better. And we would be able to get the rate constant if we graphed it by calculating the slope. Okay, so what happens if our chemical is second order? Well, this is the equation. Again, I'm not giving you the background on where these equations come from because that's using calculus. You're just going to use them. So this is the equation for second order. In some way, I've already got it rearranged in the y equals mx plus b format, so it's already there. So there's some differences. There's no natural logs in this. Instead of its inverse, 1 divided by. Another difference is in the first order, there's a negative sign right here. And in the second order, there's not. That is not a typo. There is no negative sign in the second order integrated rate law. So again, I'm going to give you these equations. You're just going to need to recognize, hey, this is the equation for second order. And hey, this is the equation for first order. You're going to need to know that as well as the values, but you don't have to memorize if there's a negative or not. I'm going to give that information to you. All the symbols stand for the same thing. Lowercase t is time. Lowercase k is rate constant. A in brackets with a 0 is the initial molarity. A in brackets with a t is the molarity after some amount of time. It's already in the y equals mx plus b form. So that means if we had to guess what we would need to put on the x and the y axis in order to make a straight line if it was second order, well, for the y-axis, it's going to be 1 divided by the molarity. And on the x-axis, it's going to be time. Okay. So that's what this is saying here. Let's look at this. Here's an equation that I'm telling you that I know is second order. And let's prove it. So this time I actually gave you the data values. So these are the data values. They did the experiment once, and they measured these 5 data points. Okay, based on time and based on the NO2 molarity. And what I want us to do is graphically figure out, is NO2 zero order, first order, second order? Really, all we can do right now is figure out first order and second order because that's all we've talked about. Okay, so to check if it's first order, what I did, this was the original data here. There we go. That's my original data. This is me taking that molarity and just taking the natural log of it. So look, I grabbed my calculator and took natural log 0.01000, and that's where the negative 4.610 came from. Natural log of 0.00787, it got negative 4.845. Okay, and then what I did was I made this my x and this my y, and this is the graph that I made. So let's look at the data points and then the red line connecting them. Is this a perfectly straight line? Well, hopefully you're shaking your head no. It's straightish, but it is still a curve. So what that tells me, well, this graph is representing first order. And the reason why I know this graph is representing first order is because the y-axis is natural log. So the fact that this is not a straight line, this chemical is not first order. That's what I learned by graphing that. I use natural log of the molarity on the y-axis, and then time on the x-axis. Once I did my graph, I did not get a perfectly straight line, so it's not first order. So now we're going to just take our data points and let's check to see if it's second order. Okay. So, again, these were the original data points. And then what I'm doing from here to here is just I'm taking 1 divided by the molarity. Okay, I just took 1 divided by 0.01000, 1 divided by 0.00787. And what I'm going to do is then make that graph where the 1 divided by thing is on the y-axis and the time is on the x-axis. And then I look at my data points, I look at my line, I see a perfectly straight line. Perfectly straight line indicates, hey, that equation works in this situation. So, which equation has 1 divided by the molarity in it? Well, it's second order. This graph was checking if something was second order. Since it made the straight line, That proves this chemical is second order because it fits. The data works. Okay, so NO2 is second order and it's not first order. I know it's second order because the straight line showed up on the 1 divided by molarity graph. And I know it's not first order because we did not make a straight line on the natural log graph. And again, the natural log, that's the equation that goes with first order. 1 divided by molarity, that's the equation that goes with second order. Okay. So then our last scenario is if something is zero order. And if something is zero order, that means you changed the molarity, the rate didn't change. So the equation didn't matter if you changed the molarity or not. So this is the simplest version. There's no natural log, there's no inverse. It's just, looks like the first order equation if we take out the natural logs. So it's also in the y equals mx plus b. So in order to test if something is a zero order, the x-axis needs to be time, the y-axis needs to be molarity. Okay, that's how we would test. And it would make a straight line. It would have a negative slope, but it would still make a straight line if it was zero order. So the way I'm going to ask these questions is you're going to be provided with, on a test question or something, 3 graphs that I've already made. One where the y-axis has molarity and the x-axis is time. The second one where the y-axis has natural log of the molarity and the x-axis is time. And one where I have 1 divided by the molarity is the y-axis and the x-axis is time. And then I'm going to say, well, I did this experiment. I collected the set of data. I graphed it 3 different ways based on these graphs. What order is the chemical? And what you will be doing is looking at the 3 graphs that were provided and finding the one, only one of them will have a straight line. So you're going to be looking for the one with the straight line. And then once you identify which of the 3 graphs has a straight line by looking at it with your eyeballs, okay, you're not doing any math here, you're just looking at the graph with your eyeballs, then once you identify the one that has a straight line, you're going to have to look at the y-axis. And depending on what's on the y-axis for the one that makes a straight line, that tells you what order the chemical is. If the y-axis is just molarity, then the chemical is zero order because it fits this equation. If the y-axis is the natural log of molarity, then the chemical is first order because it fits the first order equation. And if the y-axis is 1 divided by the inverse of the molarity, then that's second order. It fits the second order equation. That's how we're going to use this. Okay. Now, we have 2 more equations before we jump into doing our math. Okay. And that's looking at half-life. So half-life, I'm not talking about the video game. Half-life is very literally the amount of time it takes for half the chemical to be reacted. So it's how long will it take for that reaction to be exactly halfway done. Okay. Now, when we get to nuclear chemistry later in the semester, we're going to come back and look at half-life again, because that's often a situation in which they talk about the half-life. Okay. So we're going to look at it here, and we're going to look at it later in the semester. Now, the symbol for half-life is going to be T, because T stands for time, right? And half-life is the time it takes for the chemical to be halfway gone. But the symbol is T1/2. That is not the time times 1/2. No, that is just the symbol. So T with a subscript of 1/2 is the symbol for half-life. Okay. So I'm going to do a quick where this equation came from. And then I'll show you the equations. These equations will be provided for you. You don't have to memorize them. You just have to know which equation fits when and what the symbols stand for. Okay, so for a first order process, all I did here was took our original integrated rate law for first order. But instead of AT, the molarity after some time, I specifically want to know when the molarity is 0.5 times the initial, meaning half of the initial. When I do that, that's going to cancel, which leaves me with natural log of 0.5, which I can plug into my calculator, and that's where negative 0.693 came from. I'm trying to get T1/2 by itself, so I'm going to divide both sides by negative K, and this is what I'm left with. So in this equation, this is the equation that lets me solve how long does it take to get to exactly half of the chemical reacted. T1/2, the 1/2 is not a part of the equation, it's the symbol for half-life. In order to figure out the amount of time it takes for something to be halfway reacted, all I need to know is the rate constant, as long as it is first order. This works for first order only. Okay, because I used the first order equation to get this. We're going to repeat this process for second order, and then we're going to look at all of our equations, and then we're going to practice. So for second order, I took the initial equation for second order and plugged in, instead of AT, 0.5 original. Again, the point of half-life is when it's halfway done. So when our amount we have left is exactly half of the original. And then just rearrange this equation and then get it by itself. This equation is the half-life equation for second order only. And the way I remember that is, if you remember that the second order has the 1 divided by in it, that equation, the integrated rate law has 1 divided by. Well, doesn't this equation also have a 1 divided by in it, an inverse? So it kind of looks like the second order equation. We're not going to do half-life for zero order. We're just not. So you don't have to worry about that. So we've just taught ourselves 5 equations. So we're going to put them here. So if a chemical is zero order, we know the mathematical relationship between time and molarity is this. When something, and again, this equation will be given to you, is first order, the integrated rate law, the mathematical relationship between molarity and time, looks like this, where natural log is a mathematical function. And then for half-life, symbol for half-life is T1/2. The equation is 0.693 over K. For second order, the integrated rate law looks like this. And the half-life equation looks like T1/2 equals 1 over K times the initial molarity. So again, all 5 of these equations will be given to you. But when I give them to you on the test, I won't give you that header that says zero order, first order, second order. I'm going to give you a table with all of them on it, and you're going to have to know when to use them when and what the symbols stand for. I'm also not going to label the 2 half-life ones as half-life, but they will have the symbol T1/2. So as long as you know T1/2 means half-life, you're good to go. So these are our 5 new equations. We're only gonna do 3 examples, but what I want us to do is read the question. We're gonna come back and look at this slide to decide which equation is appropriate for the question, and then we'll practice doing the math. So let's look at our first one. We're supposed to determine the concentration of chemical left in a second order reaction after 25 minutes if the rate constant was determined to be 1.3 times 10 to the negative 4th inverse molarity inverse seconds, and the reaction began with 0.112 molarity. So, things I'm looking for. It very clearly tells me we are talking about a second order reaction. So when I go back to my previous slide, I'm looking at the second order column. Okay. I have 2 equations, the half-life equation and then just the regular integrated rate law equation. So I went the wrong direction. If we look at this, well, we were given a time, 25 minutes. We were given a rate constant, K, 1.3 times 10 to the negative 4th, inverse molarity, inverse seconds. We were told the reaction began with a molarity of 0.112, and that we're supposed to solve for the molarity left after time. Nowhere in that question does it say the words or use the symbol for half-life. So the half-life equation is not helpful in this equation, in this situation. So instead, what I'm going to do is at the top, write the integrated rate law. And then what I want us to do is take those symbols, and let's figure out what values go in each of their spots, and then we'll plug our numbers in and go from there. So K stands for rate constant. The question says, if the rate constant was determined to be 1.3 times 10 to the negative 4th inverse molarity inverse seconds. T stands for time. Well, the only time I see is 25 minutes. AT is the molarity after some time, which is what we're supposed to figure out. We're supposed to figure out the concentration after 25 minutes. So I'm going to put a question mark there. We don't know that one. And A0 is the initial, how much it started with, how much it began with. Okay, so we figured out our values. We know which one we're solving for. Now before oops, I realized I there. Before we go ahead and plug our numbers in, we have to double check units to make sure everything looks good. So concentrations all need to be in the same unit, so like molarity. Times need to be in the same unit. Well, in time I have 25 minutes, and for the rate constant I have inverse molarity, inverse seconds, which means I don't have the same time unit. So what I'm going to do is convert 25 minutes into seconds. So I'm going to take 25 minutes times 60, because there's 60 seconds in 1 minute. So I'm not going to show the work for that. Sorry, hopefully you're feeling okay. I got 1500 seconds when I did that. So now I'm going to go ahead and plug stuff in. So I do not know the concentration after some time. For K, I'm just using the equation up here, plugging the numbers in. 1.3 times 10 to the negative fourth, inverse molarity, inverse seconds. For T, I'm going to use the time once it was in seconds, so that when my units will cancel. And then 1 divided by 0.112. So with my calculator, I need to take 1.3 times 10 to the negative fourth times 1500, and then add that to 1 divided by 0.112. Now, I'm not going to do this each tiny step, but I'm going to say, okay, I took everything on the left-hand side and I did the math, and what I got was, I haven't rounded anything, 9.123571429. Okay. Now, if we're looking at units, I guess I forgot a unit there. The inverse seconds and seconds are going to cancel, leaving this number as 1 divided by molarity, and this number is 1 divided by molarity, so my unit is 1 divided by molarity, because I added 1 divided by molarity plus 1 divided by molarity. When we add, the units don't change. So do you think 9.123571429 is my answer? Well, I'm trying to solve for the molarity. What I have right now is 1 divided by molarity. So we're not done yet. You can think of this one of two ways. You can either say, okay, well, I need to inverse this to get that brought to the top, and then I'm going to inverse this. Or we could have cross-multiplied. Oops, not 0. 9.123571429 molarity negative 1 times AT, then divide both sides by 9.123571429. Either way, when I'm done, it looks like I only have 2 significant figures. But once I get all the way to the end with my 2 significant figures, I get 0.11 as my answer. So yes, we have to math, but we did okay. One way to check yourself, if you're a little nervous about doing the math, your initial molarity should always be bigger than, so your molarity 0 should always be bigger than your molarity T, because as time goes on, there's less chemical. So we started with 0.112 and now we're down to 0.11. It doesn't seem like a lot less, but it's a little bit less. So it's less. That means I didn't do something super weird in my math. If my answer was, if you thought you were done at 9.12, well, if I started with a 0.112 molarity and I ended with, after 25 minutes, a 9.12 molarity, how did the molarity get bigger as the reaction happened? And this was the thing we were starting with. So the chemical we start with, the amount should go down. Okay. So hopefully we're feeling okay on that with that. If not, practice in our discussion worksheet, in the practice worksheets and mastering and whatever, and then talk to me. Okay, let's go on and try another question. So we're going to read the question and then we're going to backtrack to that slide that had all of our equations and we're going to choose our equation. So a first order reaction is tested after 38.0 seconds and found to have a concentration of 0.0799 molarity at that time. The rate constant is 0.0414 inverse seconds. What is the initial concentration of this reaction? So what I know is that it's first order and that we need the initial concentration. So I'm going to backtrack. First order. So I'm looking in the first order column here. I have 2 equations. I have a half-life equation and then I have the integrated rate law equation. Well, did the question mention half-life anywhere? No. So we're not using half-life. The half-life equations, it will use the symbol T1 half or say the words half-life. So since it's first order and it's not half-life, this is the equation that we should appropriately use in this situation. What we're going to do now is figure out what our values are for each of the variables, then plug the numbers in and do our math. So a first order reaction is tested after 38.0 seconds. Well, that's a time. And found to have a concentration of 0.0799 molarity. So that's the concentration after 38 seconds. I'm putting that with the AT because that's the amount after some time. The rate constant is 0.0414 inverse seconds. What is the initial concentration of this reaction? Okay, so we've identified our variables. Now we need to plug them into our equation. So natural log of AT, natural log of 0.0799 molarity, equals negative K, 0.0414 inverse seconds times time. I guess I forgot to double check. I didn't say it out loud, but I double checked that my times were in the same units. They're seconds and inverse seconds, and that my concentration should be all in molarity. Everything looks good. Plus natural log of A0, which I don't know. Now, if the A0 makes you feel uncomfortable, like it's too scary, just write an X there. That's the thing we're solving for. Okay, so mathematically, I need to take negative 0.0414 times 38.0 to get a number here. And then on my calculator, I need to take natural log of 0.0799 and get a number here. And then what I'm going to do is I'm trying to get natural log of the initial molarity by itself. So I would add this number to the other side. So I'm not doing every single step. What I'm showing you is what, once I multiplied negative 0.0414 times 38.0, and then I took natural log of 0.0799. I'm going to take the natural log of 0.0799 minus, or sorry, plus my answer over here. I'm just getting things on the same side. Okay. So when I did that, I had negative 0.953779426 on the left, and I had natural log of A0 on the right. So do you think my answer is negative 0.953779426? No. Those units would have canceled when I multiplied them, leaving me with this natural log molarity unit. So I'm going to kind of ignore it because that's weird. But what this tells me is what the natural log of the initial molarity is. I want to know the initial molarity. So do you remember what we said was the inverse of natural log, the thing that cancels out natural log? If you ever forget, grab your calculator, find your natural log button, and see what the shift or second or whatever of the natural log button is, which is e to the x. So to cancel out that natural log, you can't divide both sides by natural log. That's not a thing. To cancel it out, you need to take e to the power of both sides. E to the power of natural log cancels out. Like taking 2 divided by 2, that cancels it out. That's how division works. Natural log is a different mathematical operation. So e to the power of is what cancels it out. So that's going to leave me with just A0 on the right-hand side. So I need to take my calculator and take e to the power of negative 0.953779426. So I'm going to use my calculator to actually do that using the e to the x function. And when I did that, I'm going to go ahead and round to 3 sig figs. 0.385 is equal to A0. So 0.385 came from me typing in e to the negative 0.953779426 in my calculator and rounding it to 3 sig figs. So here's a double check. Is my initial molarity bigger than my final or my T molarity? Well, my initial molarity I just solved for 0.385. My molarity after 38 seconds is 0.0799. Well, my initial one should be bigger than my T one because as the reaction happens, things slow down. Whew. Okay, last one. Calculate the rate constant for a first order process with a half-life of 5.8 minutes. So there's a couple of keywords in here. It's first order and it mentions half-life. So I'm going to backtrack to here. First order, so I'm looking at this one. I have 2 equations, the half-life equation and the integrated rate law equation. Since it said half-life, I'm going to use the half-life equation. So T1 half equals 0.693 over K is the equation I'm looking for. So it says calculate the rate constant, which is K, with a half-life, which the symbol for half-life is T1 half. It's 5.8 minutes. It doesn't specify units, so I can leave 5.8 as minutes. That's fine. Or if you don't like that and you want it to be in seconds, then convert it to seconds. Also fine. What I'm going to start with just leaving it in minutes. So I'm going to put 5.8 minutes right here. 0.693, and I don't know what K is, so I need to cross multiply. So I'm going to end up with 0.693 over 5.8 minutes. So in my calculator, I take 0.693 divided by 5.8, and I get 0.12. Now units, 0.693 has no units, and minutes is in the denominator, so you could write 1 divided by minutes or inverse minutes. If you decided you wanted to do things in seconds, well, there's 348 seconds in 5.8 minutes. So 348 seconds equals 0.693 over k. So 0.693 over 348 seconds. The number I get from my calculator is 0.0020, and the unit I would have no unit divided by seconds, so just seconds in the denominator. So I would have taken either one of these because I didn't specify units. Well, in mastering chemistry, they're going to specify units, so pick it. But if I don't specify units, just give me a number with the unit, and as long as you did it correctly, everything's good. So those are the integrated rate laws and half-life.